Hi, this is Alex from devstories.eu. LangGraph, episode 9 of 18. Your server crashes mid-thought while an agent is processing a massive dataset. It should not have to start over from zero. It should pick up exactly where it left off. That resilience is what we are covering today with persistence, specifically threads and checkpoints. To add persistence to a LangGraph application, you need to understand the concept of a thread. A thread represents a single, isolated execution sequence or a specific user conversation. It holds the working state of the graph as it moves from node to node. Let me clear something up right away. People often confuse thread memory with long-term cross-session memory. A thread is not a global database where your agent remembers facts across different tasks forever. It is the short-term working memory strictly tied to one ongoing sequence. You enable this memory by providing a checkpointer when you compile your graph. A checkpointer is an object that handles saving and loading the graph's state to a storage backend. Once your graph is compiled with a checkpointer, you trigger the persistence by passing a configuration object containing a thread ID whenever you invoke the graph. This ID is the unique key that the checkpointer uses to track the history of that specific run. When you run the graph with that thread ID, the checkpointer automatically saves the state. But it does not save continuously. It saves at specific boundaries called supersteps. A superstep is a distinct execution cycle in the graph. If your graph runs A followed by B, that is two supersteps. If your graph branches and runs C and D at the same time, that parallel execution is grouped into one single superstep. The checkpointer does not interrupt a node while it is working. It waits for the superstep boundary. Once all the nodes scheduled for that superstep finish executing and return their updates, LangGraph creates a checkpoint. This checkpoint contains a state snapshot, capturing exactly what the graph state variables look like at that exact moment. Let us look at how this behaves in practice. Suppose you have an agent analyzing a massive dataset. The graph has 4 steps. Step 1 fetches the data, Step 2 cleans it, Step 3 runs an expensive analysis, Step 4 formats the summary. You start the run passing a configuration with thread ID 123. The graph successfully completes the fetch, clean, and analysis steps. At the end of Step 3, the checkpointer saves a state snapshot. Then, before Step 4 can finish, your server crashes. Because you used a checkpointer and a thread ID, the state is safe. When your server restarts, you simply invoke the graph again passing the exact same thread ID 123. The checkpointer looks up the latest checkpoint. It finds the state snapshot saved right after the analysis step. The graph loads that state and resumes execution immediately at Step 4. The fetch, clean, and analysis nodes are completely skipped because their outputs are already safely stored in the thread checkpoint. Here's the key insight. By compiling your graph with a checkpointer and tying your execution to a thread ID, you turn brittle in-memory operations into durable workflows that survive interruptions automatically. That's all for this one. Thanks for listening and keep building.